This is the Component 3 class question book, question 9. The diagram below shows part of a kidney nephron showing glomerulus and Bowman's capsule, so you'll definitely recognise that, although you might not recognise these or seen these arrows before. What have we got? We have got blood going in here. This is the afferent arterial, blood going out there. This is the efferent arterial, and this is the glomerulus, and we can see ultrafiltration taking place. In here, the dominant pressure is this hydrostatic pressure, this squirty forcing of liquid. But you notice that there are some arrows going the other way, so you wouldn't really expect any liquid to be moving that way. And indeed, we have got some numbers here. This is a 2.7, 4 and 10. So most of the liquid is moving this grey arrow, and some might be moving the other way. Right, explain how the hydrostatic pressure is achieved in the glomerulus. So you know this anyway. We've got this afferent arterial there is wider than this efferent arterial, and so that creates this hydrostatic pressure. So the afferent arterial is wider than the efferent arterial. So just a bit of remembering there. Suggest which type of organic molecule in the blood is responsible for maintaining the blood osmotic pressure at 4 kilopascal. So this is going, what's dissolved in the blood that lowers the water potential or increases the osmotic pressure. So that's the same thing. So what's dissolved in the blood, and those are those plasma proteins. So what type of organic molecule is it? It's a protein, and it's our blood plasma proteins. And you, so after doing animal transport and the formation of tissue fluid, you'd know more about that as well. So we'll forgive you that one at this stage. The net movement of water is from A to B. So from A to B. Explain the processes by which some water molecules will move from B to A. So if anyone ever asks you how does water move, it can either be squirted, and that's hydrostatic pressure, or it can move by osmosis down a water potential gradient. So we've already got kind of squirty pressure, we've talked about that. So this has got to be the other one, which is osmosis down a water potential gradient. So osmosis down a water potential gradient, or from high to low water potential, from high to low water potential. Then we've got calculation. The net filtration pressure is the overall pressure responsible for ultrafiltration. From the data shown in the diagram, calculate this, and we're going to show our working and include units. The units is going to be fine. I'm going to put those in now. Those are going to be kilopascals. And so what we've got is, we've got this one's going this way. We've got from A to B. So from A to B, we've got this grey one here. So A to B, that's 10. And then the other ones, we've got this black one from B to A, that's 4. So from beta A, that's 4, and this one, where's that going? That's going from beta A as well at 2.7, from beta A 2.7. So that's our little arrow. This is our kind of grey arrow, and this is our solid arrow. And so these two are going in the different directions. So overall it's going to go from A to B because that's the biggest, but it's got to be sort of 10 minus 4 minus 2.7, and that'll be our overall pressure. So 10 minus 4 minus 2.7 is 3.3. So it's like getting paid some money but then spending some money, so it's, you know, pluses and minuses. Selective reabsorption takes place from the proximal convoluted tubule into the blood, so this is proximal convoluted tubule there, and so we're talking about reabsorption there, and this is into the, the tissue fluid or the blood. The rate of an ion from the proximal convoluted tubule into the blood was measured and showed the following trend. So as we increase the concentration, it says of a molecule or ion, it says it's an ion, so it could be Na+, for example. And you've got to think, how does this get taken up? Well, you know about co-transport, and you know about sodium ions being pumped, and then the co-transport of sodium plus glucose. Sodium will diffuse in, but only with the glucose, and then we've got a channel, facilitated diffusion of glucose. So hopefully you're thinking of this co-transport and what mechanisms. Well, here we've got active transport. This is facilitated diffusion, and here it's hard to describe, but this is kind of co-transport. But certainly I'm going to mention these two. So we've got active transport, facilitated diffusion, which means diffusion but helped by providing a route or a channel to go through. And in this cell as well we would have mitochondria. So mechanisms, active transport uses ATP for active transport. For example, I could say carrier proteins, you could say channel proteins. So these are mechanisms by which ions are moving. So probably for this ion, you're going to say the carrier protein is going to be the pump. So we've suggested some mechanisms, and now we need to sort of explain why this is leveling off. So explain what's going on there. So it's given us this information and we need to use it. Well, if we are using carrier proteins, then as the concentration of the ion that's being transported increases, then we've only got a certain number of carrier proteins, and so this will level off when they are being used as fast as they can. So it's a bit like enzyme active sites where this levels off, but this is transport proteins, but it levels off for the same reason. So graph levels off when all carrier proteins are occupied. So it's explaining that. And this type of question, we've seen it a few times in a few different questions. So you should get used to this levelling off, something being full or occupied. Suggest why glucose uptake in the proximal convoluted tubule would reduce in the presence of cyanide. If you go to your active transport notes in the core concepts, and you'll see what cyanide does. Well, cyanide prevents ATP production in aerobic respiration. So 3 marks and 3 lines here. So we need to say kind of 3. Let's talk about cyanide. So cyanide prevents ATP production in aerobic respiration. So it's actually preventing oxidative phosphorylation when you get to the second year. And why is this a problem with glucose uptake? Because glucose uses active transport as part of this mechanism. So even though glucose isn't physically transported by a pump, it's powered by active transport, this process. So glucose transport needs active transport, and that active transport needs ATP. So glucose transport, active, needs ATP, cyanide prevents ATP production. So we've got our 3 marks there. Part C, and we've got 4 marks here. We have got 3 different loops: kangaroo rat, domestic cat, beaver, and we've got these conditions. Kangaroo rat lives in the dry conditions, domestic cat in the middle, beaver in wet conditions. Different lengths of loop, and then we've got some numbers for the concentration of urine. So we can see the concentration of urine in the kangaroo rat is high, cat in the middle, beaver, low concentration. And now we just, it says using the information in the diagram. So we're going to talk about the lengths and the table. So I'm going to mention these animals, the habitat and the concentration somewhere. And then we need to relate the length to the adaptations. So, what's our starter? Longer loop, they will live in a drier environment. So that tallies. So there's a trend there. So longer loop, drier conditions in the habitat. So that's a nice easy starter there. And let's talk about this loop of Henle. So we need a little bit of knowledge here. So loop of Henle, what does that do? Longer loop, more water reabsorbed. Longer loop, more water reabsorbed. You could talk about, medulla getting a lower water potential. I'm going to put, it's not in the marks scheme, I'm going to put it in. The medulla would have lower water potential. Always try and put a bit of biology in. So urine more concentrated. So longer loop means more water is reabsorbed back into the blood, urine is more concentrated. And so we've used this information now. I could put an example in here, you know, kangaroo, rat, long loop, dry conditions, 5500, stranger unit. I'm just going to copy it. The urine. So less water lost by organisms in xeric conditions. And we could talk about the beaver possibly as well. So beaver, aquatic habitat, no need to control water, so has short loop. So we're just making sure that we're using all of this information, and trying to tie in any knowledge that we have to get their full marks.